So do we need to wait someone more? Because I see a few people that other people just started. Because usually you start at one more people. Okay, so today we continue with the design of the roof. This was the second part of the presentation that was posted yesterday evening around midnight. So finished the review at that time. I don't know if you had a chance to download it from e-learning. Please, yes. So other people like me that rather sleeping during the night are connected on the internet waiting for provide the feedback to arrive. So I posted yesterday this second part, which concludes basically the presentation of the roof, and the first part of the connection design, which will be another very big lesson. I would say the second, perhaps most important topic that we are going to deal with in this course, which is basically the design of the connections. Because as you know, like for steel, timber, it's a kind of structure, I would say it's a kind of prefabricated structure. And so it's not only a matter of designing the member, I would say it's mostly a matter of designing the connection. Because we will see that the connection very often provides the most governing, let's say, size from the whole structure. So this second presentation is starting with connection design. And we will start by seeing how we can design a carpentry connection. So connection only between good members without any steel fasteners. And we will need this first introduction about the carpentry connection to complete this work example, because if you remember, the last member that we are going to design here will be the carpentry connection between the rafter and the tile. So the carpentry connection of this king post, this truss system that make the principal load current resisting system. So now, yesterday we completed the design of the purlin, and now we go to design the principal rafter. So principal rafter will be in Italian puntone of this king truss system, which in Italian translates with what do you say? Capriato, typical capriato system. So we will have to go through different steps. First of all, as usual, we will have to calculate the most critical load condition that ultimately we state. And then, you remember yesterday we spent a good half an hour at the beginning among 21 different load conditions to find which one is the most critical one. So we can do it again today, but of course now it's easier because we know how to do it, so it's not a matter of losing too much time. Then once we design, once we assess the governing load condition, it is a matter to finding out the strength demand. So basically to solve this system, this simple system I would say. Find out the strength reaction, find out the internal forces. Then we will have to check the principal rafter design for in-plane flexural buckling. Will be, in this case, compression and bending. So we'll have I would say in Italian, instabilità a carico di punta della pressione. So this member is subjected to compression and bending in plane buckle. And then it will be a matter of finding out the problem of out-of-plane buckling. So this may buckle in plane, but can also buckle out of plane. So the out-of-plane buckling will be compression and lateral torsional buckling. Okay? So as you can see, when we talk about timber but also steel, we are very concerned about buckling, about stability basically. So we are always to check the in-plane buckling and then the out-of-plane buckling. And again, we have to make some assumptions about restraints. Buongiorno. So we will have to make some assumptions about restraints, because the most important variable, if you remember, when designing for buckling, is the effective length. Then shear strength, ultimately we state. And then the deflection control in the short and long term. So serviceability state. So we start with design load calculation. So again, if you remember, on Monday we calculated the unit weights, actually not the unit weight, the weights for units of surface, kind of pressure, if you want, acting on the roof, so permanent load. And then in order to find out the UDL, uniform distributed load on the truss system, on the truss itself, what we have to do, we need to multiply this pressure, this load, by the what we call tributary width of the truss. So the tributary width is basically the spacing between the trusses. So the trusses are spaced 5 meters. So what we have to do, we need to take, for example, the non-structural permanent load, which is 0.9 kilonewton per square meter, and multiply by the tributary width, so by 5 meters. So we get 4.5 kilonewton per meter of UDL, uniformly distributed load, applied on the truss. Then we have the structural permanent load. Again, we have the weight of the roofing, this layer of boards, 0.15 kilonewton per square meter. We need to multiply again this weight by the tributary width, so by the spacing between the trusses by 5, so we get 0.75 kilonewton per meter. We need also to add, so what we are doing now, this is basically our structure. We are assessing this load here. So, this is G2, and then G1. G1 is the set weight for the structure. So the set weight on the structure will be given by the flux, so 0.75 kilonewton per meter, and then we have the weight of the purlin. So if you remember, we have some purlins here, spaced 0.5 meter from each other. Okay? If you want to be complete, above here we have the plants. So okay, so the set weight of the plant, 0.50 meter, and we need to multiply by the tributary weight. So because we have that these trusses are spaced at 5 meters to each other. Okay. So we take the pressure, so for example, G plus 0.15 kilonewton per square meter, we multiply by the spacing between the trusses in order to find out, of course, the UDL kilonewton per meter acting on one single truss. Okay? Something that we saw 2 years ago. The reinforcement. Basic of, if you remember, when we were studying the load assessment in the reinforced concrete design, we were doing this way. Finding out the tributary weight. Okay, so this is the weight of the plant. Then we need to find out the weight of these purlins. So we have, you see, some purlins every 0.5 meters. So how can we transform, I mean, strictly speaking, those purlins, what kind of load would they apply on this truss? If we wanted to be rigorous, so if you wanted to speak with someone from mechanics of structures, what would you say? What kind of load condition we would have here, strictly speaking? We would have some point loads. Because you see, all the loads above coming from the roof is actually transmitted to the post here, to this rafter, through the purlins. So in the end, the actual scheme would be something like this, where this distance here is 0.5 meters. Okay? So strictly speaking, what we should solve is this system here, with some point loads. Okay? Now, if you remember, we also mentioned this 2 years ago, 1 year ago. If you have a beam with several point loads, you can also, by making a very little approximation, transform those point loads into an equivalent uniformly distributed load. Particularly, if you remember, I told you that if you have a beam with at least 4 point loads, this is, with good approximation, this is equivalent to a beam with a UDF. Okay? So if you have at least 4 point loads, you can transform this into an equivalent UDF. How do you calculate the UDF? Well, you sum up all these point loads and then you divide by the length. Okay? So what we can do in this case, since we have more than 4 point loads, if you check, we can directly refer to a uniformly equivalent uniformly distributed load. Now it's a matter of calculating if you want to transform the set weight of each purlin into an equivalent uniformly distributed load. How do we do this? Well, we see we have a spacing between the purlin which is 0.5 meter. So we could calculate the weight of one of this purlin. Okay, so we calculate the weight of one of this purlin because you know that we have, for example, with reference to this truss here, we will have half of the purlin, the weight transferred here will be half of the weight of the purlin going in the right direction and half of the weight of the purlin going in the left direction. So in the end, you could say that each purlin will transfer to the truss system underneath a load equal to the weight of the purlin itself. Okay. So first of all, we calculate the weight of one purlin. The weight of one purlin is the density or unit weight times the cross section, 0.14 by 0.20 times the length. So 0.70 kilonewton. Okay? So each purlin transfers a concentrated load to the truss due to its weight equal to 0.70 kilonewton. Now we need to transfer this concentrated load into an equivalent uniformly distributed load. How can we do it? Very simply. Yes, but do we really need to sum all of them and divide by the length? Is there an easier way? Yes, so if you count them, you sum, you divide by the length. Yes, so how many, we need to count how many purlins are in 1 meter. Yes, but let's say in 1 meter, how many purlins you can find? Okay, you say, okay, yeah, I have told you that. So, another one here, another one. So you say 1 meter, this is 1 meter, right? So I count 1 plus half plus half. So basically 2 purlin per meter, okay? So meaning that if I want now to go to calculate the weight, the equivalent uniformly distributed load per meter, you just double up this value here. But of course, this is simple because the spacing was 0.5. Suppose it was 0.4. How would it be done? So in this case, you can't do this kind of thing. You can't count how many those. But this is a simpler way actually. If you just think about dimensional analysis, so these are kilonewton. In order to transform this kilonewton into kilonewton per meter, what do you have to do? In this case, what I have to take as an length is actually the spacing. So if you see here, if I take 0.70 and divide by 0.5, it's like multiplied by 2. It's exactly the same. So in our case, we can do either this way, or if you want this rule, divide by the spacing, 0.70 divided by 0.5, you get exactly the same result. The second method could be useful when, of course, we don't have a simple interface or simple spacing like this, but we have a different method. Okay, so we take the value divided by the spacing. Okay, so 1.4 kN per meter. And then we still need to add the self weight of the rafter itself. Okay? So self weight of the rafter itself, again, unit weight of the boot times the cross section. So times 0.2 times 0.36, 0.36 kN per meter. Now we sum up all this contribution and we get this self weight of the structure. So 2.51 kN per meter. Okay? And then it comes to the variable loads. Snow, we know the loads. Just a reminder that this load here, 1.14, it's a load per square meter of inclined roof. Because otherwise we wouldn't be able to sum up this load here with the permanent load. Because they all refer to square meter of inclined surface, okay? So 1.14, again we multiply by the tributary width, we get 5.70. Maintenance loads, exactly the same. And wind, for the wind, we have these two loads. So minus 0.5 means that we have the wind which is uplifting the structure. So minus 2.5. Again, with the wind there is this problem. So this would be the wind. So this is what we call W1Z. And then we have the other load condition. W2Z. Now I can't remember whether we should check if this QW1Z and QWZ, if they are actually the value perpendicular to the value of the other vertical value. Can you go back and check at the beginning? Because I can't remember, I'm a bit confused with something. QWZ, yeah. So now we said the value is 0.09, which one is 0.09? This one. The vertical one. Okay, so this one, strictly speaking, and the other one, the vertical component. So this one is QW2Z, right? Yes. Should be this way, right? The number. Okay, this one. So this means that all these loads can be basically summed up together because they are all vertical components. Okay? And now we need again to go to this load combinations. So ultimately we state we have to remember the coefficients. gamma G1, gamma G2 and gamma Q. Coefficient size 0 here. Those are the loads. And those are the K-modes. We need to do exactly like yesterday. So we need to write down all the load combinations with all the possible combinations about those variable loads, like yesterday, 21. Then we need to calculate the K-mode per each load condition by taking the maximum one amount the K-mode for the different loads. And then we need to do the ratios. So we select the most critical load conditions and the one with the highest ratio between the load condition and the K-mode. Okay? So it's exactly the same procedure as yesterday. We just have to remember that we have to take either QW1 or QW2. So 21 load conditions, QS as the main variable action, QW1, then QC. Then we replace those three, we rewrite exactly the same three by changing QW1 with QW2. Again, another three. And then we start removing variable loads. So first we remove, for example, QC. We write down those four. Then we remove QW. We write down those two. Then we remove QS. We write down another four. And then we consider only one variable action, QS, QC, QW1, QW2, and last but not least, only the fragments. Okay? Also here, I think you have to, no, here you don't have to correct anything because I corrected already. This mistake of yesterday was already corrected also in this part, so now the file that I sent you yesterday is right. Is this the file sent yesterday? Or is the oldest one? No, the one yesterday. Right. So, then we calculate the different load conditions, we set the different values. And then we do the ratios with the different K-modes. So if you look at the value that we find, which is 16.5, 17.2, 20.1. So load condition number 11, which is I think the same as yesterday, should be the same probably, is 20.1. And load condition number 17, so G1, G2 and QS, again 20.1. So the most critical load conditions are the one where we consider, first of all, the most critical load conditions are the one without window, that's it. And one is the one where we consider the maintenance as a basic, as a fundamental variable load, and the other one is exactly the same number, considers instead the snow as a main variable actions and basically not the maintenance one. So the load associated with this load condition is 18.1 kN per meter, and it is distributed along the truss on the two rafters. Okay, so now what we have to do, we have a structure like this. 18.1, if I remember well, meter. So this is our structural system. We need to solve the structural system. What does it mean to solve the structural system? It means to, first of all, to find out the restraint reactions, okay? And then to solve internally, to find out the internal forces, axial force, bending moment diagram, and shear force. So now some questions for you. First of all, what kind of system is this? It's a typical truss system that you studied in statics, or not? Not really another presentation. Ingegnere, 3-pin arch, something like this. Which kind of structure is this, first of all? A truss system, but is it okay? A truss system. First of all, is it a statically determinate or statically indeterminate? So here we should be sure. Is it what? If you don't speak loudly, I can't. Don't be shy because that's not a problem. As you know very well, here you can say wrong things without any problem. Important thing in the exam, you say. So, is it statically determinate or statically indeterminate or even a stable structure? So? Indeterminate. To how many degrees? Nine, my goodness. So it means that now we need to write 9 congruence equations now. Wouldn't do so. This you can do with Professor Long. Too complex, I wouldn't be able to do it. Sorry. 3. 3 is also complex. I would struggle to write 3. 2. Now we're going down, of course. It becomes easier and easier, of course. Can we get to 0 possibly? Because 0, I do a 2, I write by 3 equilibrium equation without any congruence, and that's something that I can handle. So how do we check if one structure is statically determinate or statically indeterminate? The degree of freedom, so we should write the degree of freedom of 1, 2, 3 bars, 9, and the restraint. So it's 1, 2, 3, the number of degree of freedom of those 3 bars, which are rigid, is 9 in the plane. Okay? Now we need to see if we have 9 restraints for this. So this one takes away how many degrees of freedom? 3. Then we have another internal pin. Are you sure that this takes away 3 degrees of freedom? Two degrees of freedom, this one. Because this allows only the rotation. Yes. So 2 here, then 2 here, 2 here, 6. So 9 minus 6 equal 3, and then we have the external restraint. This one. This takes away how many? How many?
2 internal and 1 external.
The external. So now what we counted now was this, and this. And then we need to count this one and this one. So the roller, how many degrees of freedom take away the roller itself?
Can you repeat?
Yes, now we are counting, since we are not sure whether this system is a statically determinate or statically indeterminate or even unstable, we are counting the degrees of let's say the restraint degree, the number of degrees of freedom that are cancelled out by the restraints. So we have actually we have 3 internal pins, okay, and then we have 2 external restraints. So we need to count how many degrees. So we said each internal pin takes away 2 degrees of freedom. So if you want, you do an equation like number of degree of freedom equal, we said 3 times 3, 9. Then number of degree of restraint, we said 2 times 3 because we have 3 internal pins. And then we have 1 roller and 1 external hinge. So the external roller, how many degrees of freedom takes away? This one. 1. Okay? Sorry, plus 1. And this one? 2. So 9. Now the degree of hyperstaticity, there's a big awkward word, but let's say this way, is number of degree of restraint minus number of degree of freedom. 9 minus 9 equals 0. Okay? And I'm happy. It means that I need not write any congruous equation. Okay? So this is a statically determined system. In fact, if you think about, you also do something like this. You can first isolate this and check if this is behaving like a rigid body. It is. And then, of course, this rigid body must be in some way connected, must be restrained in order not to move into the plane. Okay, so this is a statically determinate system. Now, the question is this a truss system? Which were the hypotheses that you made in statics to solve a truss system? Can you tell me?
It's not a truss system because we have a load on the beam.
Exactly. That's a real point. What you study in statics were truss systems made of beams and pins, like this. But one of the hypotheses was that the loads were concentrated loads and were all applied where?
The nodes.
On the nodes, so on the pins. Okay, so this is not a strictly speaking, this is not a truss system. If it was a truss system, so if the loads were applied to the nodes, you knew that as a property of the truss system, what kind of forces can you expect into the beams? Only axial force, either tension or compression. In this case, is that since we have a UDL, what we can expect in the beams?
Bending moment.
We can expect also bending moment and shear. Okay? So in this sense, this is a non-typical truss system. So how can we solve now this system here? In order to find out the bending and the shear, what we need to do something like this. We need to say that first we transform this into, well, we have to transform this into a transistor. How can we transform this into a transistor? We can think about adding one additional restraint above that. Okay? If I add an additional restraint here, then you see this one become a beam, normal beam like this. Statically determinate beam that I can solve without any problem. Okay? But of course here I have introduced a restraint which is not there in the reality. So I will find here a reaction. Then I have to solve the other system. And I will find another reaction there. So in order to now to go back to the original system, what do we need to do? We need to remove this one, this restraint, and to apply the reaction changed by sign. So basically the opposite reaction. So I can say that this one, if you want the original system, this one is equal to the superposition of two different systems. One, like this. Plus another one with which dot condition here? To make this superposition equivalent to this, which kind of dot do I need to put there? So, which one?
On the top.
On the top here, I need to put a concentrated load given by what? Let's say this P here equal here we have R1, here we have R2 equal to R1 plus R2. Strictly speaking, you should say minus, okay, if you want to be rigorous, it will be minus R1 minus R2, because we have to take the other side. Okay? Now this one, it's a truss system. Yes. This one is a truss system I can solve as I know, with the methods that we learned in statics. This other one, but this is simply supported beam, so I can split them, I can solve without any problem. Of course, here, in this system here, what would be the stress within the, sorry, in this system here, you want to be rigorous, sorry, you should say, this is R1 here, R1, R2. So in this system here, what would be the stress distribution within this tile here? Nothing. Okay? So this is unloaded. Instead, this one will be loaded because we have the loaded line in the basically in the internal beam. Okay?
But we can disassemble the structure.
Well, we can.
Disassembling the structure.
Well, we cannot understand. Why we can't understand the structure?
Risolve il problema statico per ogni asta rispetto.
Yes, so I don't understand this comment. So what you're saying, did you make something wrong or not?
No, it's correct, but it's more difficult.
Then what? What is the other option?
Solve any element separately.
Yes, but to solve this one, How can you solve this separately? I don't understand.
Faccio l'esploro.
Yes, of course, you can do it. To me, this is the simplest way, because otherwise this one, you need to write, since this one is not a normal beam, in this system here, you need to add then the, I don't know what you call it, the auxiliary equation, because you have more. Because this one it's a clause, it's not a beam. No, you need to write down then the auxiliary equation. You can do also this way. Write down the auxiliary equation, that's it. But to me, it's simple to do this way. Because this one is very simple to solve. I don't even need to do the intersection here. I just decompose this 4C in the two directions. Here we use the equilibrium, the node, and this is the negative solve. And this one is a simple supported thing. So QL squared divided by A. Instead, how would you do that? How would you do this? You would start from this one. And so okay, first you find the restraint reaction outside, this is simple. And then inside you need to find out, yes, the different, yes. You also go this way.
Noi prendiamo una struttura e la suddivisiamo in due sottostrutture per avere una trave, cioè per avere una trave.
No, praticamente sì, questa qui, siccome questo non è una trave reticolare, quindi a rigore non è che posso applicare direttamente tutte le forze, no? Cioè il metodo delle forze eccetera, l'idea è quella di trasformarla, di metterci un vincolo qui e quindi creo la mia trave inclinata, quelle quadrato ottavi, taglio qui. Dopodiché le reazioni vincolari le cambio di segno, le metto in cima qui e mi risolvo la curvatura reticolare. Le due strutture sono equivalenti, no? Non c'è, o meglio, cioè questa struttura qui è equivalente alla sovrapposizione di queste due. The other option, like your colleague said, is to start immediately from this one. You can start from this, and then for the symmetry you need to start to do a cross section. So in this way you need to do a cross section because you need to open. This is a closed structure. So first you need to open. So you need to do a cross section. For example, you do a cross section here. But when you do a cross section here, do you know the horizontal component? No. No. So you need to write an auxiliary equation to find out this component. You know? So this was instead here I don't write any auxiliary equation here. So that was the reason why. Of course, after if you use some 2000, of course you don't need to do anything. Just put inside your structure, and some 2000 will solve for you everything. But you have to do by hand. I found it easier to do this way here. Once we accept and we understand that the sum of the solution of those two structures is equivalent to the solution of the original structure. In other words, when you have a structure, you can always add, if you want, a restraint, solve this structure, and then of course you need to superimpose the solution with another structure where we have applied the restraint reaction opposite. Okay? So it's okay. Do we have any doubt about this? Are you convinced, or you have doubts about what we've done here? Okay, so this is the original system, you said. This is the superposition between these two systems. So the restraint reaction 72.4 because you multiply T.1 by 2, so 36.2, and you times 2 because you have also been on the other side. So restraint reaction of this system, very simple, 18.1 times 4, the length divided by 2, 36.2. Then we have to solve the system. We need to find out the bending moment diagram and shear force diagram, the axial force diagram. So this is the reference line, 36.2, 36.2. this 36.2 has two components. If you decompose the 36.2, you get 18.1 in one direction and 31.4 in the other direction. Okay, so 36.2 times, this is the inclination here at 30 degrees, so times the cos of 30 degrees will give us 31.4, which is the shear, the value of the shear. 31.4, 31.4. And then, of course, there is also an axial component, as you can see. So the axial component is 18.1 because it's 36.2 times sin of 30 degrees. So 30 degrees, sin of 30 degrees is 18.1. So I still see some discussion about which stuff we have. Which stuff we have. Com'è? Ma su questo? Che numero?
Non ho capito perché devo guardarsi, perché fare questo quali secondo me non esiste.
Per lei allora mi spieghi come è più semplice? Sì, vabbè, ma c'è la cerniera, quindi devo scindere in due, cioè come faccio? Cioè, no, è possibile anche così, assolutamente, non è... Però come lo risolvo? Sì, però un elemento, questo qui è libero. Cioè, come fate a crearsi una reazione? Cioè, lo può fare, ma deve scrivere una reazione così, una concentrazione ausiliare, no? Cioè, questo qui... Quindi qui sono queste inconnute, no? Quindi se io scrivo l'equazione di equilibrio, io ho 4 inconnute, quindi una non me la do. Poi devo scrivere un'altra. E poi devo fare quella dall'altra parte. Quindi voi descrivereste tutte le equazioni di equilibrio di quella. Descrivete tutte le equazioni di equilibrio. Quindi avete 1, 2, 3, vabbè, quindi vi scrivete 3 equazioni di equilibrio su questo, 3 equazioni di equilibrio su questo e 3 qua. Semplificate e trovate la soluzione. Sì, sì. Yes, the remark is that we could also disassemble the system in these 1, 2, and 3 bars and write all the equilibrium equation here and solve them. This could be also an option, yes. Sì, sempre c'è yes, there is always. Maybe it's not in the drawing, but there is a alternative. Yes. Come?
Questo schema l'ha visto
Guarda, così diciamo subito. Prima? Yes, here there is a pin. So it's missing. So add one pin here and one pin there. So basically we have two methods to do this. One method is the method that I follow, is this one, for me it's easier. But the remark is that it may be simple to use this other one. I agree, I mean, you can use whatever method you want as long as you get the right solution, so I don't care.
No, because we never use this.
This method here, yes.
Never use.
Never use. Okay, if you never use, it's better to use this one. Do this way, you don't get wrong. Of course, both are equivalent. Perhaps this one is more mechanics, what you have already done. This one is a bit, you may see a bit strange, because you have to add a restraint to take it away and so on. Okay, anyway. So now, if you were to use this method here, first we need to solve the system, the beam, which is a simply supported beam. We need to, of course, refer to the fact that this restraint reaction here, they are inclined. So we will get a shear component, and we will get also an axial force component. So I think what 1 kilonewton. So how does the axial force diagram, how does the axial force vary in this system here? You see here we have 31, here we have compression, so minus 18.1, but equilibrium would be 18.1 times sin of 30 degrees times x, where x is the distance here. The shear force diagram, again, we have a linear trend, and the bending moment diagram will have a parabolic trend. So in the end, those are the force diagrams. So axial force, shear, and bending moment. Axial force, we have first, we have compression here, and then we have tension on the opposite side. The moment is always positive. Maximum axial force, minus 18.1 kilonewton compression. Maximum shear force, 31.4 kilonewton at the support. And maximum bending moment at mid-span, 31.4 kilonewton per meter. Now we need to solve the system number 2. So please add also here the pin. There's always a pin there on the top. In this case, the solution is very simple, because you see, if you do the equilibrium of the joint number 1 here, it's just a matter of basically decomposing this force, 36.2, which is a restraint reaction, along those two directions in order to get the axial force in the rafter and the tensile force into the tie. So the tie being tensile force will be NT, so 36.2. So R12 will be equal to the axial force, so 36.2 divided by tangent of 30 degrees, so 62.7. And the compression force in the rafter will be 72.4. Also here we can draw the diagrams. So axial force diagram, 72.4 compression in the rafter, and 62.7 of tension in the tie, and of course nothing in terms of axial force, sorry, in terms of bending moment and shear force, because this is a truss system. So we are expecting a truss system only axial forces, nothing else. Maximum tensile force will be 62.7, maximum compressive force will be minus 72.4. Okay? Cosa sei? Manca la faccia niente,
No, cioè non ho capito da dove vengono poi questi.
Okay, so we go back. Another time we'll do this other method. Next year we'll do this method. So this 72.4 kilonewton, this is the restraint reaction coming from, go back. Coming from here, 36.2, and then you have another system, exactly the same, another 36.2.
Okay.
So basically it would be, when I add this restraint here, I found this restraint reaction. Since in the reality this restraint is not there, I need to solve another system where I have applied the restraint reaction but opposite. Okay?
Professore,
Yes.
nella slide precedente, quando si deve calcolare il sforzo assiale del cambio, qui
Here?
avanti.
Avanti.
Sì, quello del ricorso sarebbe il contributo del carico e l'uso del carico.
Yes, this would be the contribution of the uniformly distributed load, only of the axial component of the uniformly distributed load.
Per la cooperazione portata statica.
Sì.
Noi avevamo lo sforzo normale, cioè questa cooperazione che avevamo normalità del momento, però qui sul taglio
No, sul taglio, ok, sul taglio, no. On the shear, there is a slightly different convention in mechanics of structure and in structural design. Usually in structural design, the shear is positive in one direction, but I know that in mechanics of material, we learned that it's positive in the opposite direction. Okay? No. Anyway, the shear, the sign of the shear is not important. So you can use one convention, you can use the other one, nothing changes. Because for the shear, it's not important the sign. The sign is important, compression, tension, so axial force, and it's important for bending, not for shear. So for shear, you can use any kind of convention that you want without any problem. We are just doing this way because, you know, from when I started studying this kind of matter at the high school, we always use the same kind of convention for the shear. But I know that here you use another one, but this doesn't change, doesn't change at all. Because for the shear, the sign is never important. If you think about when you do the shear verification, you never have to put any sign inside. Okay? So don't worry about the sign. You can use your agreements, I mean your convention without any problem. This is not a, will never be a mistake. Okay? Okay, so the type intensive force, this I think we've already done before, if you remember well. The diagrams. And then we need to do finally the superposition between the two systems. So if we superimpose the diagrams of axial force, shear force, and bending moment, we get this diagram here. So you see, here we have in system 1 we have a linear diagram, and in system 2 we have a constant one, so we get this trapezoidal diagram. Shear and bending moment were only in system number 1. So maximum compression force, you see, is at the base, 91 kN. It's important also to get the compression force at midspan. Why? Because at midspan we have the maximum bending moment. So maximum bending moment, 31.4 kN per meter. Here we have not only bending moment, but we have also the axial force. An axial force of 73 kN. Oh, and if you can correct, actually I also correct immediately. Here is the sign, the minus is missing there. So let's put the minus to the other one. Maximum shear force 31.4 at the support. So having a distribution of internal forces like this, where are you going to check the safety or ultimate mistake of the router, in your opinion? Which section are you going to do it? So where are we going to do the ultimate mistake control for a rafter having this distribution of forces? Okay, so at the midspan for sure, because we have bending, maximum bending, and we have a high compression force. Only this? What do you mean the same for shear? Okay, so which other section are we going to check? Here, for shear. And then, are we finished or we need to do one more check? So we say midspan for bending axial force. Support for shear. Something else? Yes? This is buckling will be included, if you remember, the buckling is included in this check that we are going to do for bending and axial force, because we need to calculate the sigma, and then we need to reduce the strain by this K factor that will take account of the buckling. So when we do buckling, we always have to choose one cross section. So cross section, we said we check the cross section halfway, mid-span. This is okay because I have the maximum bending moment. We also have an important axial force, so it will be pressure pressione, so couple bending moment, axial force. We set the shear at the support. Do we need to check another cross section to be sure that nothing is going to happen? Maximum compression. Where do I have maximum compression? At the support, here. So we need to do one more check at the support there, when we have also maximum compression, even though there we don't have any bending moment. So probably the most critical will be at mid-span, but we don't know. We need to check. Because at mid-span we have a maximum bending moment, we have a high value of, you see, a high value of 73 of compression. But we don't know a priori, so we need to check also the other cross section where I have the maximum bending moment, so the maximum axial force. Okay, now we start with the verification. We said first in-plane flexural buckling. What does it mean in-plane flexural buckling? It means that what we are going to check now is buckling. So if this is our cross section, this is Y, and this is Z. Which kind of buckling are we going to check when we talk about in-plane flexural buckling? What do you think? Well, yes, both cross section, but buckling around which axis? So if we talk about in-plane, in-plane means buckling around, yes, but in-plane, it means in the plane of the structure. So it will be around Y, okay? So buckling around Y means that this beam is going to deflect vertically, so it will deflect in the plane of the structure. So this will be in-plane buckling, quindi stabilità nel piano, instabilità nel piano. And then we have to check also out of plane, which means around Z in some way. So buckling outside of the plane, okay? So, in-plane flexural buckling. We said before, we need to check two sections. The mid-span, where we have maximum bending moment and we have a significant axial force. Now here I didn't put the sign anymore, okay? Just you have to remember that if you want to put, for your sake of clarity, put it. Actually, we also put here, so we have no doubt. Just remember the minus refer to the fact that we have compression. So, mid-span, maximum bending moment, and a high value of compression. Lower support, no bending moment, maximum axial force, compression. Those are the formulas according to the Eurocode 5. So, of course, these formulas are for both buckling around Y and buckling around Z. And of course, in this case, you see there is also this additional component taking into account the problem of biaxial bending. But in this case, we don't have biaxial bending. So we are talking about, in this formula here, you see there is the slenderness ratios, the relative slenderness ratio, the ratios of gyration, and so on. So, in our case, we have symmetric bending. So what we need to check is this design inequality here. So you see, this is the compressive stress in the timber due to the loads, in this case it would be due to the compression, divided by the reduction coefficient due to buckling times the compressive design strength of timber, plus the ratio between the bending stress of timber and the bending strength of timber. The sum shall be less than or equal to 1. So this is the kind of control that we need to do for in-plane flexural buckling. So, of course, this is the best thing to do is to have a spreadsheet. So breadth of the cross-section, depth, the length. In this case, you can assume a buckling length. I mean, the length could be the length of the whole beam, basically. Imperfection. This beta C is an imperfection coefficient. You see, this beta C is an imperfection coefficient which affects this Ky coefficient. It's equal to 0.2 for solid timber, 0.1 for blue laminated timber. So this coefficient takes into account the fact that the beams are not always straight. They always have an initial curvature, which is going to reduce, of course, the critical load. So for solid timber, 0.2. These are the geometrical properties of the cross-section, and then we can calculate the compressive strength, the bending strength of solid timber C18, characteristic module of elasticity, modification factor, safety factor, size effect, and then here you have the different components, the slenderness ratios. So in this case we are talking about this slenderness ratio here. So the lambda that we refer to is lambda y. So it's a buckling for bending around y. And in the end, you see that you get a reduction coefficient of 0.9. And so we have a safety factor of 0.78. So in the end, this verification of in-plane flexural buckling at midspan is satisfied because we have a safety factor of 0.78. And we can arrive up to 1. Then we need to do again the same check at the base of the rafter where we have the maximum compression and no bending. In this case, you see the safety factor is much lower. So 0.13. Meaning that actually, strictly speaking, this would be the opposite of the safety factor. We should correct this actually. Safety. Because safety factor, this is usually safety factor should be higher than 1. Anyway, this one, 0.13, which is called safety factor here, is nothing more than this ratio here. Go back one. Here. So will be basically this ratio here. This ratio shall be less than or greater or equal than 1. So in the first case we get 0.78 when we check at the span. In the second case, when we check at the base, when we have a slightly higher axial force but not bending moment, we have much less because we have 0.13, meaning that we are far away from the failure. Okay, so the first check is okay. In plane flexural buckling is satisfied. Then we need to check the structure for out of plane buckling. So for compression and lateral torsional buckling. So from Eurocode 5, those are the formulas that we already saw. last time for lateral torsional buckling for a beam. And if you have that your beam is not only loaded by bending but also by compression, then you see you just need to take this ratio. So if there was no compression, you should just check the sigma MD, so the maximum bending stress. You divide it by the reduction coefficient times the bending strength. This should be less than or equal to 1 if there is no compression. If there is also a beam which is subjected to compression, you need to take this ratio, take to the power of 2, and sum this other coefficient, which is a ratio between the maximum compressive strength divided by the reduction factor for buckling out of plane times FC0D. Okay? Now we are checking again, we are checking the out of plane buckling. So we are checking this possibility. That's our cross section. Y, Z, and Z. So this cross section, so this is the cross section of the rafter, the puntone. This one could buckle out of plane in this way. Okay? While instead before, we check this possibility. Buckling in plane. So buckling in this direction. Okay? This is before and this is now. So we need again to check what is the effective length for lateral torsional buckling. Now I ask you, in your opinion, for a structure like this, what is the value of the effective length to consider? We are checking this member, which is also the other one, of course. So a structure like this, how can it buckle out of plane? I mean, before, when we were checking the in-plane buckling, it was quite clear that this would be the buckling length. Couldn't be anything different, because this one is restrained by this, and this member is restrained by the other one. But now we are checking out of plane. So now we need to look not in the lateral view, we need to look down to our structure. So looking down, this is one truss, then here we have another truss, then here another truss, and those trusses are connected by the purlins. Now we ask to ourselves, what is the lateral, the effective length out of plane? So in this direction. Clear my question? Is the question clear first? Yes. Now we need to think about the possible answer. Yes, the question is, we need to assess the effective length for lateral torsional buckling. The regulation said the effective length will be we need to decide, of course, the type of load that we have. In this case, a uniformly distributed load, so it will be 0.9 times the length plus, if you remember, twice the depth of the member, which is not very important in this case, but of course we can write it. The problem is, which length should I assume now? This is the length for buckling out of plane. So I can't refer to this figure here. I need to look down to my structure. You need to understand, if I look down, this is my structure, which length should I consider? Should I consider a possibility to buckle in this way, for example, or in this way, or in this way? purlins are rigid, fully rigid. Okay? Let's start with this one. They are not, but suppose that the purlins are fully rigid. The last one, this one. But are we sure that if the purlins are fully rigid, this is okay? The purlins are fully rigid in this direction. Are we sure that this is enough to prevent this possibility? What do you mean for travel translation? Which one? This is our structure, this one. This is our structure. Looking down, we have the two pitches, 1 and 2. One is this way. Okay? So, remember that for lateral torsional buckling, to choose this length here, or to choose the other one, we bring to completely different results. In one case, in this case here, we wouldn't have any lateral torsional buckling, practically. In the other way, probably, well, we will have for sure, and we need to see if we can deal with that or not. So even if those purlins are fully rigid, are they able to prevent a buckling like this of everything?
No, not able.
Eh?
They are not able.
They are not able. They just transfer this lateral deflection to all the other trusses. So we have that all the trusses are buckling simultaneously. Okay? So the purlins alone are not enough to some way to prevent this possible lateral torsional buckling, not only of the rafter but of the other frame in this case. Okay? So what do we have to do if we want to prevent this kind of buckling, which would be quite critical? What can we do? So? To put some bracing. How can you put this bracing? First, we need to identify which. We need to think about also the size of the structure. This is not a huge structure like last time, 20 meters by. This is a small structure. It's 2 pitches. So we're talking about, I think, 4 meters by 5. So we could think about putting, for example, a bracing like this. So one cross bracing on one pitch and one cross brace on the other pitch. If I do it this way, what could I do if I put this bracing? Which kind of deformed shape can I draw? Can I expect? So is this possible? No. Which are my fixed point right now with this cross bracing? Is this fixed? This one is fixed? Why not? Is this fixed? Yes. This fixed? Yes. So the deformed shape will become this one. What about this now? Is this possible? So this one is going to buckle this way. What about the other one? Now, if I put a bracing here, I'm sure that this is fixed. Of course, also this is fixed. So here I have perhaps another. No, my question is, what about this?
Not possible now.
No, it's not possible. What?
The big.
Why is not possible?
Because now the purlins are fixed.
Now the purlins can work. In the reality, they will never be rigid, fully rigid, but for sure they will have some strength to make also this point get fixed and also this one fixed. So now all the trusses are fixed in the eve of the, so here, that will become fixed here, here, and here. So now, the length L to put inside there will be basically this one. We want this one. Okay? So, yes. Yes, so instead of two crosses, so my suggestion is what's happens if I do a cross, if I use a diagonal bracing. It's like what you are saying, that's something else.
Abbiamo due campate con
This one.
come quella però non ci stanno tre campate, ma solo due. Uguale la stessa struttura. Dice doppia croce, abbiamo il secondo turno. Senza l'ultima campata.
Yeah, okay, but then the structure goes continue this way. Okay. In this case, what you are doing, you are using a diagonal system. Yes. In this case, again, something like this. Yes. Of course, what will be different, the design of the diagonal will be different in this case compared to before. Yes.
The distances will be bigger.
So basically, instead of this, we are talking about removing these two and putting them here. No, it will be exactly the same. They are always non-tension system because it resists. For example, if I have a deformation like this, yes, they are always non-tension system. The same. Okay. Another possibility would be, like we were mentioning yesterday, to replace the layer of boards with an in-plane stiff system. For example, with plywood panels, or with OSB panels, or with cross-lamp panels. So, on top of the pyramids, rather than having small boards, which makes this roofing unstable, to use panels like this, so big panels. So sheets or sheathing of wood, 1.2 meter times 2.4 meter, nailed all around the perimeter. Okay? So replace the small and narrow boards with two-dimensional panels. If you do so, this can provide some bracing to hold the roof. And in this case, we can also say that the length L becomes basically zero. So we have that our rafter is supported along the whole length. In this case, strictly speaking, it would have been zero, would be the distance between the pyramids. It would be 0.5 meter, which means that basically we would have the drop. Okay? Because the pyramids are there connected to a rigid plane, an in-plane rigid, made with these panels. Okay?
For this system,
Which one?
this is that you are design. We have to put in 4 vent system.
No, we can also put, you mean 4 rods here? No, I mean, what do you mean 4? This one? 1, 2, 3, 4, this?
No, 4 controllati, cioè 4 controllati. No.
No, this, for me, this one is 2 bracing. This is 1 and this is 2. What do you say 4?
E non altri 2 sulla...
No, this one was an option that your colleague asked. He said, instead of putting 4 bars here, can I put 2 bars here and then 2 on the other one? Yes.
Quindi
But this was another system, so without the bars, so we said either we put the bars and we leave the boards above, or we don't put the bars, we replace the boards with this two-dimensional sheathing system, plywood, okay? There are two options. If we use one, we don't need to use the other one.
Quindi ci avessimo messo solo controversia, avremmo 4 di quelle X.
No.
E bastavano solo
Ne bastano solo due. So the question is this: if I have a structure which, let's suppose that here you have 10 trusses. You have 10 trusses. Do you need to put these bars in each of these 10 trusses? No. You just need to brace one, two, let's say two, and then all the others, since they are connected with the purlins, they are all fixed. Basically because they are connected with the purlins. Okay, it's clear? What could happen is that when you go to design this bracing, it could happen that you get very big cross section. If you have, let's say, if you have 20 trusses, by using only one bracing or two bracing here, you will get very big cross section. And so in this case, it's better perhaps to have to use either 2 or 3. Okay? Yes, but if you do this, it's not because you have to. It's just because the size may become big of the rod. But strictly speaking, you just need one. And then all the others that are connected with the purlins, they are okay. Okay? It's clear? So we said in our case, the length is now the length between these points here. So basically it's the length of half of the truss, because we have put the bracing. So basically what we have done is see something like this. Or like you were saying, you can also remove 1 and 2 and put in the other one. You said. Okay? So looking down, this is our situation. And of course we said that this would be the length to consider. So the length is only 3.5 meters. Of course 3.5 is in looking down in plan, but we have to consider that in elevation it's longer, it's 4 meters, so we need to consider 4 meters. Again, if you replace all the properties inside here, we get to see a safety factor of 0.63. This shall be less than 1, so lateral torsional buckling coupled with compression is not an issue for this kind of structure. Okay? Okay, any question about this? Everything clear? Okay, now next check is a shear strength at ultimate mistake. For shear strength, we found that the maximum shear is always at the ends of the rafter, 32.0 kilonewton. The verification, we need to calculate the maximum shear stress and compare with the resisting shear. We have to remember we always have to apply this reduction coefficient equal to 2/3 for the shearing area. So the maximum shear, in this case we need to keep in mind that we have biaxial bending. So due to biaxial bending, we have two shear components. Oh no, sorry, now we are talking about the rafter. For the rafter we don't have biaxial bending. We have uniaxial bending, so for the rafter is only one shear component, is this one. The double shear component was yesterday when we were talking about the purlins, of course. So the maximum shear you see is 3 divided by 2 times T divided by TF times H, 1 Newton per square millimeter. And then we calculate design strength, shear strength, to 2 Newton per square millimeter. So the verification is satisfied. For shear, we need to use the shear resistance for longitudinal so parallel to the grain, FPK. In the end, you see the shear verification is satisfied. And then we have to do the deflection control in the short and in the long term at serviceability limit state. We start with the deflection control in the short term. We need to consider the characteristic or real load condition. Those are the values of the loads. So we have these values here, those we found before. Yeah. We need to consider always to ignore the favorable loads. So for the check of the deflection in the short term, the regulation, the Italian regulation says that we should refer only to the variable components of the characteristic load condition without the favorable variable load. So QW1 is not considered here because it's uplifting. Those are the 3 loads to consider, 3 load combination. And of course this, when we consider the wind acting downwards, strictly speaking, we have always the 2 components, but we already saw yesterday that one is -0. If we replace the variable with the number, we find out this value that you can find here. So if you look at the highest value, it's by far the first one. So the load combination 1 is the one having the snow as a basic variable load, and the wind, only 60% of the wind. Strictly speaking, there will be a component along Z, and there will be also a component along Y, but the component along Y is very small. So those are the 2 components. Fz, so we have, if we consider the vertical component, Fz can be decomposed into one component perpendicular to the roof and the other one parallel to the roof. So the one parallel to the roof is, you have to multiply by sin of 30 degrees, so it's 3 Newton per millimeter, and the other one is that perpendicular to the roof is 5.2 Newton per millimeter. Then we have this other load in the horizontal direction, very low, 115 kN per meter. Also this one, strictly speaking, we should consider 2 components. The component along the roof, y direction, minus 113 because it's opposite to the other one, and the one vertical, which is 0, the one perpendicular to the roof, which is 0.08 Newton per millimeter. So for short-term deflection, this force here is 5.2 Newton per millimeter. The other one is 0.08. So in the end, it's 5.28. So it's basically, if you go back, if we sum this component here with the one that we had before, with this one, we get this value of 5.28 Newton per millimeter in Z direction, so the direction perpendicular to the plane of the roof. This will be used to calculate the deflection. So in the short term, we have to use, as usual, the mean value of the shear modulus of elasticity, the mean value of the Young modulus of elasticity parallel to the grain. We need to calculate the first moment, so the second moment of area around Y, and then we can use this formula here, exactly like we did yesterday for the instantaneous deflection. we take the properties from this table, as usual. And so if we sum up those two deflection components, we get to a deflection here at this value of 2.85 millimeter. The limit is the length divided by 250, so 16 millimeter. As you can see, we are far away. So this kind of structure, the deflection is far away from the limit in terms of short-term deflection. Then we need to control the deflection in the long term. For the long term, we need to consider both the characteristic and the quasi-permanent load conditions. Like yesterday, for the quasi-permanent, the variable loads do not produce any creep because the cycle coefficients are all 0. So we need, that done yesterday, we need to calculate first the instantaneous part of the deflection and then the creep part. For the long-term deflection, for the instantaneous part, as usual, we consider all the unfavorable loads, so the permanents, both permanents and the wind load, the downward wind load, the maintenance, and the snow. We have also here 3 load combinations like before. And then we need to do the creep component. The creep component is taken from the quasi-permanent load combination. We have only this basically, so all the unfavorable loads combined together. So the long-term deflection will be the sum of the short-term deflection due to the characteristic of condition plus the creep deflection due to the quasi-permanent combination. The short-term deflection due to the characteristic of condition is the sum of the short-term deflection due to the only permanent loads plus the short-term deflection due to the variable loads that we calculated before. That was 2.85 millimeter. For the short-term deflection due to the permanent load, we can use, like yesterday, the superposition principle. So first we calculate the value of the load, the permanent load, so 70 kilonewton per meter in the z direction. This load must be decomposed in the z asterisk direction, so perpendicular to the ground, perpendicular to the floor, and in the other direction. So again, if we replace, if we calculate again all these properties, geometrical properties, with this formula here, the deflection due to the permanent load is 2.87 millimeter. Then we need to calculate the creep deflection due to the quasi-permanent load condition, which is the creep coefficient times the instantaneous deflection due to the quasi-permanent load condition. So basically this W quasi-permanent condition is the same that we have just calculated, 2.7 millimeter. Okay, then the creep coefficient is 0.8, and so if we replace the value, we get altogether 8 millimeter of deflection in the long term. The limit is 20, so as you can see, we are far away from the limit also here. So the long-term deflection control is satisfied. Okay, now to conclude, we just missed the tie beam, the design of the tie beam, and then next time we can start with the connection between the rafter and the tie beam. So for the tie beam design, we have to go through the ultimate mistake design load calculation, strain demand, and laser strain verification. But actually, these first 2 bullet points were already solved before. When we solved the whole system, we already got the ultimate mistake design load and the strain demand. So for the tie beam, for catena in Italian, we got this diagram here. So axial force 62.7 kN in tension, 62.7 kN tension. So what we need to do is just the verification for ultimate release state of tension. So strength demand 63 kN. We need to calculate the tensile stress parallel to the brain and compare with the tensile strength parallel to the frame. So we just calculate the cross-sectional area. So sigma t 0t is the axial force divided by the cross-sectional area. We get 0.9 Newton per square millimeter. The calculation now of the tensile strength by using all these coefficients from the Eurocode file, the characteristic tensile strength of this timber is taken from the table. So it's 10 Newton per square millimeter. So we get, divided by 1.5, we get 6 Newton per square millimeter. So in the end, this is tensile strength, you see? Tension parallel to the brain 10. So 0.9, maximum stress, 6 strength. So the tensile, the ultimate limit state of tensile strength is satisfied. Okay? So with this, basically, we have completed the design of the roof in terms of permit and truss system. The same, rafter and beam. And now, next time, on Monday, we will start dealing with the connections. So we will have a first introductory lesson. The last presentation that I uploaded yesterday was about talking about connections, so carpentry connections. And then as soon as we finish this introductory lesson about carpentry connection, we come back here and we do the check for the carpentry connection. Okay? Good. Thank you very much and see you on Monday.